Welcome to session 3 of the Generalized Method of Moments lecture. And here we will actually outline, what is Generalized Method of Moments. In the preceding session, we just talked about method of moments. The only twist here will be a little bit of subtlety on essentially the weight matrix. So to start, let's define a function. It's actually a vector-valued function, a q/1 vector of functions describing independent information regarding the relationship between y and parameters theta. Now, theta can be a vector, so let's say it's a p/1 vector of parameters. So we have a q/1 vector of functions relating a p/1 vector of parameters. Q equations, p parameters. And so long as q is greater than p, we should be able to get a solution for our p theta values. Now let's say that the expected value of these function f are equal to 0 if and only if theta is equal to theta naught. So that essentially our moment equations, or population moment equations, their expected value is 0 at the population parameter and not otherwise. If you are thinking about some function g where y is related and that function is equal to some constant that's not equal to 0, well then f could simply be g minus b. So you can always convert it into a function with that actually has an expected value equal to 0. So let's let capital M of theta be defined as the expected value of these moment equations. If M of theta is equal to 0 only at the true value, then it's identified. And we can define the following. Some matrix Q such that, or some value Q such that M transpose WM is 0 only at theta naught, the true value, for all positive definite matrices W. This is that quadratic expression in which W is a positive definite matrix, and that means that the MWM quadratic is only equal to 0 at theta naught, and Q is greater than 0 for any theta that's not equal to theta naught. Consequently, Q is minimized at the true value. Now, if we let little m be the sample moment analog to it, then we can say that theta hat is our generalized method of moments estimator, and it is that value that minimizes the sample moments. So again, our little q is our sample moments. These should be little m's here. The quadratic equation sample moments. Now, if we take the derivative of this equation, we get the derivative of the moments with respect to theta, transpose times W times the moments, and it's equal to 0 at the minimum. Right, this is what would be the case for a local minimum interior point. So what are the properties of this estimator? Well, first, the estimator is consistent. So for this to be the case, we have to have proper specification, which means the population moment condition, so that the moments in the population sense is such that Q at theta naught is in fact equal to 0. We need it to be identified as stated above, so that M at theta is equal to 0 means that theta is in fact theta naught. And both the identification and the fact that W is positive definite implies that Q is greater than 0 for all theta that's not equal to theta naught, and therefore theta naught is the minimizing value of the capital Q, which is, say, the population moment equations. So the intuition behind consistency is that if our estimator, theta hat, is the value that minimizes the sample moments, And if the p-lim of the sample moments goes to the population moments, Q, well, actually this is the quadratic function in the sample moments, and if that quadratic function goes to the quadratic function in the population, and as stated above, if theta naught is in fact the value that minimizes Q naught, then the p-lim of the generalized method moments estimator theta hat is in fact Q naught. Right? All we're saying here is that the estimator theta hat minimizes the quadratic in the moment conditions for the sample. The p-lim of the sample goes to the population moments. I guess technically you could say goes to the data generating process moments. And theta naught is the minimizing value of those moments, therefore the p-lim of theta hat is actually equal to theta naught. There's some technical issues having to do with it's valid on the type of convergence of Q to capital Q. Q is uniformly convergent to Q. We have the data are independent, or they're what's called ergodically stationary. We won't worry about those nuances for this particular lecture. And that the moment conditions F are regular, which is to say that F is continuous on the parameter space theta for all possible data, and F is well behaved, which is to say that the expected value exists and is finite for all theta, and the expected value is continuous on theta. Population moment conditions underlying this estimator is, again, specification. Has to be correct. And if they're correct, then the expected value will equal to 0. Identification globally, which is to say that the expected value is not equal to 0 for any theta that's not equal to theta naught. Local regularity, so that we can essentially draw solutions by using the derivatives, is to say that the derivatives of f with respect to theta exist are continuous. And theta naught is an interior point of the parameter space, and the expected value of the derivatives are finite. Local identification conditions is that the rank of the expected value of this set of derivatives is equal to the number of parameters p. If you don't have at least p amount of information, which is to say p equations of independent information, then you can't solve for the p parameters. That's essentially what it's saying. And our matrix Wi associated with any given data set converges to a positive definite matrix. These actually only have to be semi-positive definite, but it needs to converge in probability to a positive definite matrix. The parameter space is compact, and our function f is essentially bound by a finite expectation. It's bound with a finite, bound by a function with a finite expectation. So it doesn't essentially go off into infinity anymore. The generalized method moments estimator is also asymptotically normal. Asymptotically normal with a mean of the true value and a variance v, where the variance v is 1 over the sample size g transpose wg inverse, where g is the probability limit of the derivatives of the moments with respect to theta. It is optimal if w is set to simply the inverse of the variance of the moments. Look at this in a little bit more detail. We can use the trick of appealing to the mean value theorem, which says that there is a value theta bar between our estimator theta hat and theta naught, such that the moment at theta hat is equal to the moment equations at theta naught plus g theta hat times theta hat minus theta. If we were to multiply both sides by g transpose w, so you notice we did this with both sides. this first term by the first order conditions above for the maximum is equal to 0. And so that this whole side here is equal to 0. We can solve for our theta hat minus theta. Multiply by the square root of n. We have the square root of n, theta hat minus theta, is equal to this term g transpose w, g inverse, g transpose w times the moment conditions times the square root of n. If we collapse this whole component here up to the moment conditions into a label f, then we have, actually without the minus, we have minus f times the square root of n moment conditions. So with the central limit theorem, if the expected value of the outer product of the moment conditions are finite, and the limit of the variance of the square root of n times the moment conditions go to a positive definite matrix, then the square root of n times the moment conditions is normal, normal, mean of 0, and variance s. Now, g at theta hat goes to g at theta naught. This is because theta hat is consistent estimator, and therefore g of theta bar also goes to this, because remember theta bar is sandwiched between theta hat and the true value. So we essentially just have our g function, which I'll drop the theta naught component in here, and f then above is simply g wg inverse times g transpose w. This is a constant matrix. So essentially we have the square root of n of theta hat minus theta is a constant times the normal 0 with variance s. So it converges to a normal f s f transpose. This is a way of, in matrix notation, squaring the constant, putting the f and f transpose on the outside. What is s? Well, s, as stated above, is the limit of the variance of the square root of n times the moment conditions. So the limit as n goes to infinity of the variance of the square root of n times 1 over n times fi, these are our sample moments, is 1 over n, the variance of the summation of I fi. And the limit as n goes to infinity, therefore 1 over n times the variance of the summation. So what is that? Well, for each observation, fi, we can look at, and then some other observation fj, we can look at essentially the expected value of the cross products, which is some matrix sigma ik, I guess I did jk, and essentially the overall across the observations is the variance covariance matrix within observation on the diagonals, and then the variance covariance matrices across observations on the off diagonals. So if there are n observations, it's an nq by nq matrix. If we set up a matrix with a double I guess I'll call it, I don't know what to call it, matrix, is essentially taking a identity matrix, diagonal ones, for each of the a q size ones for each of the observations 1 to n, and stack them into this kind of big matrix. Then essentially the variance of the sum of the fi is equal to that I transpose sigma I. This is just a way to essentially sum up all of the variance covariances in that matrix of variances and covariances. So S is equal to 1 over n times this particular matrix. Now, if the observations are uncorrelated, such that all of the off-diagonal matrices here are, oops, that's not an off-diagonal one, all of these off-diagonal matrices are all 0, and it's just block diagonal, right, with the matrices going down the diagonal. Then S is even simpler. It's just simply the sample average. It's the sum of the variance covariance matrices for each observation. Right, now each observation, you can see, well, is a set of data, or the realization of a set of data, and it has Q moment conditions applied to those X's that essentially comprise those data. So you get a sigma II for each individual in the data set or each observation. You sum across them and divide by 1 over n. So our square root of n, sigma hat, is our estimator, minus the true value, converges in distribution to a normal 0 FSF. F is this big matrix here, where again G is 1 over n times the summation of the derivatives of f with respect to theta. This is a Q by P. And it's minimized at W equal to S inverse. So if you set W equal to S inverse and you work through that FSF transpose matrix, it will come down to simply equal to G transpose S inverse G, that whole quantity, to the inverse. You can estimate G by 1 over n times the summation of the derivatives of the moment equation with respect to theta for each observation. Let's put a little I up here, F, evaluated at theta hat. And you can estimate S as 1 over n, the outer product of the F's. So, which if you were to, for independent observations, set up a set of variables, one for each of the Q equations, and a rows equal to the number of observations, then S hat is simply 1 over n H transpose H. So what you do is you estimate theta hat first using W equal to the identity matrix. In other words, remember, all you need for a consistent estimate of the generalized method of moments estimator is a positive definite W. Well, the identity matrix is positive definite. So you can estimate theta hat, and based on theta hat, you can calculate the S above, and you can get, therefore, a new weight matrix. And then using that weight matrix, you can estimate theta hat again. And you can iterate this process to convergence. And that is a way of estimating generalized method of moments, where you start with an identity matrix, and then you use the information from that to create a better matrix and iterate yourself to a solution. So this ends the third session of the Generalized Method of Moments lecture.